Hello viewers, Daruna taking you through the story for A-Level Physics Paper 2. And this video we are going through the topic of magnetism and alternating current, and in particular calculations on electron dynamics. So this video is suitable for students in both Senior 5 and Senior 6 offering physics as part of their combination. So this is what we hope to upload. What is ticked means it's already available on the platform. What is not yet ticked means will be uploaded with time. And here we are interested in calculations, but complete notes are available in the books I recommend. For physics, there are 4 books: Physics Part 1, Physics Part 2, Topical Question Bank and its solutions. Mathematics Principle, there are 4 books: Math Part 1, Math Part 2, Timely Pacifiers Marking Guides, and Topical Question Bank. Subsidiary Math is only 1 book which contains both notes and past papers. So for any of the copies, contact the author on this contact. So electron dynamics in a magnetic field. In other words, how do electrons behave when placed in a magnetic field? So this video is broken down into 3 parts. The first part is this one, which is force on charges moving a magnetic field. Then next is an electron moving in a magnetic field, and the last one is about Hall effect. We shall see all in this video. So we shall consider a conductor of length L carrying a current I in a magnetic field of flux density capital B. So let's try to draw the diagram. That will be a conductor of length L. It's carrying current, so this will be the direction of the current. And we know that electrons move in an opposite direction, in a direction opposite to that of the current. So if current is moving in this direction, electrons should move in the opposite direction. Then that will be the magnetic field of flux density capital B. At an angle of this, making an angle of theta degrees with the conductor. So suppose that there are n free electrons in this conductor. It implies that the total charge is equal to Ne, where E is the electronic charge. But it's also equal to I.t, where I is the current, T is the time taken. So making I the subject, I'll come up with Ne over T, which is this. So here T is the time taken for each electron to move across the conductor. Then drift velocity will be distance over time, where the distance is the length of the conductor. This is the time taken. When I make T the subject, I'll come up with L over V. So charge flowing, charge flow rate. So rate of charge flow rate is the same as Q over T. Now Q over T Now Q over T is the same as I. If you look at this formula, if you look at this, do you see Q is equal to IT? Okay, now charge flow rate means Q over T, meaning that I will be left with I. That's why you see here the charge flow rate is current, and this current will be equal to Q, this is Q, over the T, which is this, Q over T, which is here. Division sign becomes a multiplication by getting the reciprocal of this. So when I combine them, I'll come up with Ne V over L. Therefore, the total magnetic force exerted on n electrons will be given by BIL sine theta. I think you remember this formula, I already covered it under the first video. So B is there, I is here, and L then sine theta. So there I realized that this and this can cancel. So I remain with Bn EV sine theta. But N is the same as capital Q, so I'll come up with BQV sine theta. So that will be the formula for force on charges moving in a conductor. So generally, a charge Q moving perpendicular to the field of flux density B with drift velocity V has a force given by that. So where there is theta, you put there 90 degrees, you come up with this. When I make B the subject, I'll come up with another expression for magnetic flux density. Remember previously, we had seen that F equal to B I L, you could make B the subject. That gave us one definition of magnetic flux density. But now here also, when you make B the subject, we can come up with another definition of the magnetic flux density, which is force when charge is 1 coulomb and V is 1 meter per second. Okay, so force on the charge moving in a magnetic field is 0 if the particle is moving along, not this word, along the magnetic field. Because along the magnetic field, it means that the angle between the field and the conductor is 0. And it's maximum when it's moving perpendicular to the magnetic field, meaning the angle is 90 degrees. Then another note is that for a single electron, Q will be equal to E, because you know that Q is equal to NE. So when it is one electron, it means that N is equal to 1. That's why you say that Q is equal to E. That means that here in the formula for force, we replace capital Q with E, like that. So when you see us using the formula BEV sine theta, it means that they are considering only one electron. Then from this expression, you can get the second definition for magnetic flux density, which will be the force exerted on a charge of 1 coulomb moving with a velocity of 1 meter per second perpendicular to the magnetic field. So the key word is that this, what is in the denominator, should be 1 coulomb 1 meter per second. And because there is no sine theta, it implies the angle should be 90. That's why there is the word perpendicular here. Then a Tesla, remember Tesla means that, in this case a Tesla, think like I told you previously, to define an SI unit, it means that all expressions should be 1. So if I have B, Q, V. In your definition, I need to hear you say 1 Newton somewhere. You should also talk about the flux density being 1 Tesla, charge being 1 coulomb, and V being 1 meter per second. Let's see if all those ones are talked about in this definition. So it says a Tesla can be defined from this expression as the magnetic flux density in the magnetic field when a force on a charge of 1 coulomb, see that? So this has been covered before, moving with a velocity of 1 meter per second, that V is covered before, at right angles, so the 90 is covered before, to the field is 1 Newton. 1 Newton. So 1 Newton has been catered before. So that becomes a Tesla. Because when this is 1, this is 1, this is 1, then even B should also be 1, like that. Okay, so with that, you can go through these questions. Question 1 says, a particle with charge this is moving with a velocity of this in a magnetic field of flux density 0.3 Tesla. calculate the force on the particle if the velocity is perpendicular to the magnetic field. So shall I quote the formula? Because they say perpendicular, theta is 90, that's why you see us just using B to V. Substitute for B, which is flux density, substitute for charge, substitute for velocity. You'll end up with the force they wanted. Question 2. An alpha particle of charge this is moving with a velocity of this, perpendicular to a magnetic field of 0.4 Tesla. Calculate the force experienced by the alpha particle. So force is B to V, flux density, charge, and velocity. You'll come up with the answer they wanted. Then question 3 says, a particle with charge this is moving with a velocity of this and experiences a force of this. Calculate the strength of the magnetic field, that is now flux density, if the velocity is perpendicular to the magnetic field. Perpendicular means we use B to V, then substitute for the force, for the charge, and for the velocity. You remain with B as the only unknown, so you can make it the subject, and that's what they wanted. Question 4. An electron with charge this is moving with a velocity of this at an angle of 45 degrees to the magnetic field of 0.2 Tesla. Calculate the force on the electron. So here they are considering only one electron, meaning you can now use BeV sine theta, where B is the flux density, E is the electronic charge, which is here, V is the velocity, which is here, and theta is the angle, which is here. Then question 5. A particle with charge this is moving with a velocity of this in a non-uniform, know that word, non-uniform magnetic field that varies from 0.1 Tesla to 0.4 Tesla. Okay, calculate the average force experienced by the particle. So first of all, we need to get the average flux density by summing up the minimum plus maximum over 2. Minimum is here, maximum is here, divide by 2, you get the average flux density. Now it is that average flux density which you use to get the average force. So B average times charge times the velocity to give you the average force. Question 6. A particle with charge this is moving with a velocity of this in a non-uniform magnetic field which varies from 0.2 Tesla to 0.5 Tesla. Calculate the average force experienced by the particle. So this is similar to the one we've just done. First get the average flux density by sum divided by 2, then use it to get the average force, and that's what they wanted. Then question 7. A particle with charge this is moving with a velocity of this in a magnetic field of 0.2 Tesla. The angle between the velocity and the magnetic field varies from 30 degrees to 90 degrees. Calculate the range of forces experienced by the particle. So you'll get when the angle is 30 degrees, B to V, so flux density, charge on the particle, velocity, and theta will be 30. You come up with this. Then also when the angle is 90 degrees, we shall come up with, so we shall change theta where theta will get put there 90 degrees, you'll come up with that. Then they ask for the range of the forces. So the forces range from this up to this, and that's what they wanted. Question 8. A particle with charge this is moving with a velocity of this in a magnetic field of 0.2 Tesla. The angle between the velocity and the magnetic field varies from 45 degrees to 90 degrees. Calculate the range of forces experienced by the particle. So still we'll do the same. When theta is 45 degrees, you come up with one force, which is minimum. Then when theta is 90 degrees, you come up with the second force, which is maximum. Then you can conclude the range of forces are from this to this, and that's what they wanted. Question 9. A particle with charge this is moving with a velocity that varies from this to this in a magnetic field of 0.5 Tesla. Calculate the range of forces experienced by the particle if the velocity is perpendicular to the field. So when v is 1 exponent 6, the force will be that. We're not adding there sin theta because the field is perpendicular. When v is 3 exponent 6, the force will now be this. So the side range of forces then, meaning you can now conclude to get the range of the forces. Question 10, it says a particle with charge this is moving with a velocity of 4 exponent 6 meters per second in a magnetic field that varies from 0.1 Tesla to 0.4 Tesla. Calculate the range of forces experienced by the particle if the velocity is perpendicular to the magnetic field. So when B is 0.1 Tesla, force will be that, and when B is 0.4 Tesla, force is that. Therefore, the range of forces will be from this up to this. So that was force on a charge in a conductor. Now we shall go to deflection of an electron by a magnetic field. So consider a stream of electrons entering normally into a field of magnetic field, into a uniform magnetic field, which is perpendicular and directed into the plane of the field as shown below. So that will be uniform magnetic field. This will be the electron. It goes, it enters the field, it follows its path, and it also comes out of the field. So by Fleming's left-hand rule, we can get this as, this will now be the force. According to this rule, you realize that, remember we said second finger is current, first finger is field. That's why your first finger is field, it's pointing into the plane. That's why you see, you cannot see this first finger because it is pointing into the plane. Then the second finger is pointing in the direction of current. Because this is the direction of electron, current should be opposite. So the direction of an electron and the direction of the current are opposite each other. So electrons are moving to the right, current should move to the left. That's why you see second finger pointing this direction. When that happens, you realize that the thumb points downwards, and that will be the direction of the force acting on the electron. This one shows the velocity as it enters. Then when it enters, it keeps on being deviated. So at point set D, still the magnitude is the same. Realize that magnitude is the same, but direction has changed. When magnitude is the same but direction changes, means that now that is circular motion. So we can conclude that an electron follows a circular path inside a magnetic field. So when these are elongated, you come up to the center, meaning this is the radius of that circular path. So the electron beam describes the circular path in a magnetic field, which can be explained as follows. So current flows in the opposite direction to that of the motion of the electrons. And applying Fleming's left-hand rule, the force on the electron is downwards, and the electrons are therefore deflected downwards, describing a circular path. Considering one electron, circular motion will be maintained if the magnetic force provides the necessary centripetal force. And magnetic force already saw that it's given by BeV. Now we are not adding there sin theta because of the condition we wrote at the start. We talked about perpendicular. So here we shall just say BeV is equal to the necessary centripetal force. So where B is the magnetic flux density of the given field, E is the electronic charge and is constant, V is the drift velocity of the electron, M is the electron mass and is a constant, R is the radius of the circular path described by the electron. Therefore, when the electron moves out of the field, the magnetic force becomes zero, because magnetic force acts within a magnetic field. Know that word? Magnetic force acts within a magnetic field. So when it leaves that space of the magnetic field, there's no longer magnetic force. Therefore, the electrons move along the straight line, which is tangential to the circular path at the point of exit, at the point where they left the magnetic field. Okay, so with that, we can now go through the calculations. Question 1 says, a proton with charge this is moving in a circular path of radius this, with a velocity of this in a magnetic field. Okay, calculate the magnetic field strength required to maintain this circular motion, and it gave you mass of electron, mass of the proton is this. So you need to remember the condition for circular motion to be maintained, that the magnetic force provides the necessary centripetal force. So come and substitute to come up with this. Then from here make B the subject, meaning these two go down to come up with this. Then you substitute mass of the proton, drift velocity, charge, and the radius to give you this as the magnetic flux density. Then question 2, a proton with charge this is moving in a circular path of radius 0.2 meters with a velocity of 1 exponent 7 meters per second in a magnetic field. Okay, calculate the magnetic field strength required to maintain this circular motion. So still consider the same. For circular motion to be maintained, magnetic force provides the necessary centripetal force. Therefore, come and substitute for magnetic force and equate it to centripetal force. Then make B the subject to come up with this. Then substitute for mass, drift velocity, charge, and radius to give you the required magnetic flux density. Then question 3 came from UNEB 2015 paper 2 question 5 Roman 2 and says a charged particle of mass 1.4 exponent negative 7 kilograms, negative 27 kilograms, and charge 1.6 exponent negative 19 coulomb enters the region of uniform magnetic field of flux density 0.2 Tesla at a point P, which is this, and emerges at a point Q as shown below. Okay, if the speed of the particle is this, calculate the distance PQ. So that is what we know. And the particle describes the circular motion of radius r. So let's see how that happens. We are just redrawing the given diagram. Then after drawing it, we shall show the path taken by the electron. So that means that from P to Q it was circular. And because it is circular, it should come from it should have a center. That circle should have a center. That center is here, meaning this is R, this is also R. When that happens, it means that this is an isosceles triangle. And for isosceles triangle, it means that when this is 90, this is also 90. When this is 45, this is also 45, like that. So if this is 45, this is 90, it means that even here there will be 45. Meaning this angle will also be 45, alternating. Also here 45, 90, this will be 45. Meaning that this angle is also 45, like that. So for circular motion, magnetic force provides the necessary centripetal force, meaning I can make R the subject. So that will be the R, but remember the distance they want is distance PQ. So once I know R, I can use Pythagoras theory because this angle is already 90. Come up with the required distance. Next, we shall talk about what we call Hall effect. So Hall effect is the appearance of a small potential difference across the sides of a current carrying conductor in a magnetic field in a direction at right angles to the field. So appearance of a small PD is what we call the Hall effect. Now what is Hall? That PD is then what we call Hall voltage. So Hall voltage is the maximum PD set up across a conductor when a perpendicular magnetic field is applied. Uses of Hall voltage: 1, to determine the number of charge carriers per unit volume, to find the sign of the majority charge carrier in a given material, and to determine the magnetic flux density in the conduct in which the conductor is placed. So let us try to derive what we call Hall voltage, that small voltage which appears in presence of a magnetic field. So we shall consider a rectangular strip of metal carrying current I in the y direction. Okay, suppose the magnetic field of flux density B is applied normally to the metal strip as shown below. So I need to draw to make an illustration. So that will be our strip, thickness is D and width is T. So you're connected to a power supply, which is now called which will give us what we call the whole voltage. Now because of this one will create a negative charge. So negative terminal will create negative charge here, and positive terminal will create a positive charge at Q. Now those two charges create what we call electric field. That electric field creates an electrostatic force. Now remember, we have we have been dealing with what we call magnetic force. That is the force in an electric field. Sorry, force in a magnetic field. Then when we talk about electrostatic force, we're talking about force in an electric field. So in this case, there is an electric field because of this difference in potential and a separation. That means there will be an electric field intensity. The force is acting downward because, remember, this is a negative charge. An electron is negatively charged, meaning it will be attracted towards the positive charge. Think you remember that in the laws of electrostatics, where they say unlike charges attract while like charges repel. So this electron will be repelled by this negative charge, but it will be attracted by this positive charge. Now that force will be given by electric field intensity times the electronic charge. It is only one electron. Then we have current. If we pass current in that direction, when we pass current in that direction, it means that now the electron will move, because we said, I don't remember previously, we said that current and electrons move in opposite directions. So when I introduce a current in this direction to the right, okay, it means that this electron has to move to the left. That's why you're seeing the drift velocity of this electron is to the left. Now let us also introduce in what we call magnetic field, which is this. When introducing that magnetic field, there will be a magnetic force, but that magnetic force is got by Fleming's left hand rule, where the second finger shows the direction of the current, first finger shows the direction of the field, and the thumb is pointing upward, meaning that the magnetic force is upward. Okay. So when current I begins flowing through the conductor in the direction shown by Fleming's left-hand rule, the magnetic force BeV acts on the conducting electrons in the direction towards the upper face P of the metal strip. We have seen that. Electrons are thus deflected towards P, since the electrons are deflected towards P, and since there is a high concentration of negative charge on P and positive charge on side Q, a potential difference develops between sides P and Q. Okay, the charge separation causes an electrostatic force. E electric field intensity times E, which is the electronic charge, in the strip which opposes the magnetic field. I think you saw that in the illustration. The flow of electrons ceases when the EMF reaches a particular value VH. The flow of electrons ceases when the EMF reaches a particular value VH, and that is called Hall voltage. Now let us see how do we calculate Hall voltage. Okay, so the appearance of the voltage VH is equal to ED electric field intensity times D. How does it come about? Because we know that E is equal to V over D. Okay, meaning that when I make V the subject, this will go this side to come up with E times D. Across the metal strip called the Hall effect. So that appearance is what we call the Hall effect. When the electrons are in equilibrium, know that word, equilibrium, okay, it means that the electrostatic force on the electron is equal to the magnetic force on it, i.e. electrostatic force equal to magnetic force. E cancels, so remain with E is equal to BV. But we know that E is equal to VH times over D. Therefore, come and substitute where there is E, you put VH over D. You realize that drift velocity, which is V, is equal to Hall voltage over B times D. So this is what we call drift velocity of the electrons. So if drift velocity is given, you can get Hall voltage by cross multiplying, isn't it? Because this will now be BVD equal to Hall voltage. But I've given you this expression because sometimes they can ask for drift velocity of the electron. Okay, so given that D is the length of the strip and T is the thickness, cross-section area will be equal to T times D. And from never, this is, I think you got it, and you remember this under current electricity. Current is equal to never, which is number of electrons, electronic charge, drift velocity, and cross-section area of the conductor. So what I'm going to do, I'm going to substitute for drift velocity and for area. When I do that, I realize that something cancels, D will cancel. So in the end, I can make VH the subject. So making it the subject, I'll come up with BI over net. So I look at two expressions. One was drift velocity and the other was Hall voltage. Both are vital. But there's something you need to know about the N. N is the number of free electrons in each 1 meter cubed. So it means number of electrons per unit volume. N means number of electrons per unit volume. Okay, now we can do these questions. Question 1 says, a certain semiconductor which is rectangular in shape with a thickness of 1 millimeter is held in a uniform magnetic field parallel to the thickness of the semiconductor. The magnetic flux density is 0.4 Tesla. If the current passed is 1 ampere, the Hall voltage developed is 0.28 millivolt. Calculate the number of electrons per unit volume of the semiconductor. So we know that thickness is that, current is that, flux density is that, Hall voltage is that. Therefore I can code the formula for Hall voltage and make N the subject. When I make N the subject, I come up with this. So substitute for flux density, current, electronic charge, Hall voltage, and thickness. You'll come up with that as the number of electrons per unit volume. Then question 2, a metal strip of 2.0 centimeters wide and 0.1 centimeter thick carries a current of 20 ampere at right angles to a uniform magnetic field of flux density 2 Tesla. The Hall voltage is measured to be this. Calculate Roman 1, the drift velocity of the electrons. Roman 2, the number of free electrons per unit volume on the metal strip. And Roman 3, the electric field intensity between the length of the strip. Okay. So that is what is given. So Roman 1, drift velocity, we know the formula for drift velocity. So substitute Hall voltage over flux density times length, which gives you this. Then Roman 2, drift velocity, Hall voltage is that. So I can make n the subject to come up with the number of electrons per unit volume. Then they also ask for the electric field intensity. I can either get it from here by saying VH over D, or I can remember what we wrote previously. We said E is equal to BV. Substitute B and V, you'll still get the same answer. Then question 3, a metal strip 120 millimeters wide and 0.4 millimeters thick carries a current of 2 ampere at right angles to the field, to a uniform magnetic field of flux density 2 Tesla. The Hall voltage is 4.27 microvolt. Calculate Roman 1, the drift velocity, Roman 2, number of density of charge carriers in the strip, and Roman 3, electric field intensity between the length of the strip, or the width. So that is what is given. Then I can calculate drift velocity, substitute Hall voltage, flux density, and the width to give you this, or length. Then Roman 2, make n the subject, you will still come up with the number of electrons required. And Roman 3, electric field intensity, there are 2 formulas, you can either use that or you can use this. Whatever you use is okay. So that brings us to the end of this video.